So we're continuing talking about the chemistry of life, and we can't talk about the chemistry of life without talking about water, because you guys know water is one of the most important molecules of life. All life began in water because of water, and all organisms are 70 to 90% water, including us humans. Water has a very interesting chemical makeup. So first, let's draw what the bond would look like for water. And by the way, guys, water is H2O. That means it has 2 hydrogens and 1 oxygen. So here's what water is going to look like. First, we're going to draw our oxygen atom. All right, so here's our oxygen atom. If you look at the periodic table, you see oxygen has 8 electrons. So it has 2 in its first shell and then 6 in its second shell. So what oxygen needs is it needs another electron here and another electron here in order to make it have a full octet. So what will happen is now you're going to have 2 hydrogens come in. Each one of these hydrogens has 1 electron. And remember, hydrogen needs 1 more electron in order to have a full valence shell. So this hydrogen and this oxygen are going to share this set of electrons, and this hydrogen and this electron over here are going to share. So what you end up with is the 1 oxygen and a single bond onto a hydrogen and another single bond onto a hydrogen. Now, what makes this molecule really special is that the oxygen really wants these electrons a little bit more than the hydrogen does. So the oxygen steals a little bit extra kind of these electrons, and that gives the oxygen a partially negative charge. And the way that we show this is we write this weird symbol that looks like this. I'll show you in the next slide. So oxygen has a partially negative charge, and the 2 hydrogens end up with a partially positive charge. So what you end up with when you have water, you have a whole bunch of these, water molecules, oxygens bound to hydrogens. But what happens because this oxygen has a slightly negative charge and these hydrogens are slightly positive? You always have to remember opposites attract. So what you end up with is another water molecule over here, and the hydrogen, which is slightly positive, is attracted to this slightly negative oxygen. And you're going to see that all over the water. When this hydrogen from one water molecule is attracted to the oxygen of another molecule, they form a bond, and we draw it with a dotted line. This dotted line is a special kind of bond called a hydrogen bond. Remember I told you at the beginning of this chapter that there's 3 types of bonds. We already talked about ionic covalent, and the third is the hydrogen bond. So this is what the hydrogen bond looks like. It's a hydrogen that's temporarily attracted to another molecule, usually an oxygen in water. And we always draw these hydrogen bonds as dotted lines because they're really, really weak and they're only temporary. This is like the hydrogen and the oxygen went on like one date. They're not like going to get married or anything. So they're just temporary bond, but then they're going to break and this water is going to go find another water molecule to hang out with. All right, so overall, water is made up of an oxygen that's covalently bonded to 2 hydrogens. So when you see the solid line here, you know that's a covalent bond, but there also might be some different water molecules that are temporarily attracted to one another, and those are the hydrogen bonds. So here's an example of what a whole bunch of hydrogen bonds would look like. This is what liquid water looks like when you're drinking water. All these water molecules are all floating around and they're all temporarily attracted to one another, and they're all very close together. When water turns into ice, these hydrogen bonds become almost a little bit more stationary, but also the water molecules will separate apart and they'll form this cool looking ring thing. But it's all just temporary. If the ice melts, then these hydrogen bonds will break. Here's a super cool video I found. These are a bunch of water molecules that are forming into ice. So you can see when they're water, it's temporary bonds breaking and forming. And then when they form ice, they form like those ring-like things, and the hydrogen bonds are a little bit more permanent. So whenever you have a molecule, such as water, that has one side that's slightly negative charged and one side that's slightly positive charged, these charges are uneven charges. Then we say this molecule is polar. Polar means uneven charges. On the other hand, a molecule that's non-polar would mean that the electrons are shared shared equally in the compound. So for example, methane, which we drew the other day, that has it's a carbon with 4 hydrogens. This one is non-polar. All the electrons are shared equally. The main molecule that we'll ever talk about that is superpolar is water. Water is superpolar. Now, one other important thing about water is a great solvent. What this means is other things can dissolve really easily in water. Like we talked about, salt can dissolve in water. Sugars can dissolve in water. So this makes water a solvent. Other things will, dissolve in there. Now, anything that is attracted to water, it loves water, is called hydrophilic. Whenever you see hydro means water. Whenever you see anything that says phile or philic, and a lot of biology words have this phile at the end, it means to love. So hydrophilic means attracted to water. It's a molecule that likes the water. Anything that's hydrophobic, it's the opposite. It hates water. Now, the main type of molecule that really hates water are fats and oils. As we'll talk about later today, fats and oils hate water. They are not attracted to it. That's why when you get salad dressing, you see like the oil will separate from the rest of it and you'll have to like shake it to mix it up because fats and oils hate the water. Now, the next thing we need to talk about quickly is the pH scale.
And I'm sure you've seen this before, but let's just go through it one more time. So the pH scale ranges from 0 to 14. Right in the middle here, if it's between 6 and 8, it's considered to be neutral, where the pH of 7 is exactly neutral. Anything with a pH lower than 7 is considered to be acidic, and anything with a pH higher than 7 is considered to be basic. A substance that is acidic, or an acid, what makes it an acid is it has a very high concentration of hydrogen or protons. All right, so H+, this indicates hydrogen cations. So if you want to make a solution more acidic, that's all you have to do is add some hydrogen cations to the solution. Now, if you want to make a solution more basic or with a higher pH, you have to add what's called the hydroxide ions. Hydroxide ions are OH-, okay? Oxygen, hydrogen with a negative charge. They're anions, okay? So anytime you see a hydroxide ion, you know that would make a solution more basic or a higher pH. Now, in terms of the human body, there's a couple of important pHs to remember. The first one is human blood. Our blood always needs to have a pH around 7.4. It might fluctuate a little bit, like 7 to 7.6. You should be okay. The other one is our stomach acid, which can have a pH as low as between 1 to 2. It's a very acidic solution in your stomach. And the reason your stomach acid is so acidic is because that is one of the ways that helps digest the food you eat. Now, like I told you, blood pH needs to remain around neutral, around 7.4. If the blood pH becomes too acidic, it can lead to a really dangerous and even life-threatening disorder called acidosis. So acidosis is when the blood pH becomes lower than 7 or critically low. Usually if someone is in a state of acidosis, it usually indicates like a kidney or a breathing lung issue. Some signs of acidosis: someone may feel nervous system signs like confusion, headache, or even coma if it's very severe, muscle weakness, perhaps diarrhea, nausea, and vomiting. The heart rate will increase. They may feel respiratory symptoms like coughing or shortness of breath. On the other end, if the blood pH becomes too high, it can lead to the opposite, alkalosis, which is when the pH of the blood is very basic or above around 7.6 or higher, so when the blood pH is too high. Similarly, this is usually caused by some sort of kidney or respiratory problem. Now, luckily in your body, you have these molecules called buffers, and buffers, they work to help keep pH stable. So the job of the buffer is always to stabilize pH and maintain it to where it needs to be. So in our body, for example, in our blood, Buffers act to maintain the pH at 7.4.
And as always, there are some review questions here, which we'll go over in class.